Okay, this is our second lecture for the um, section on uh, right angle trigonometry, unit circles, and vectors. This whole unit is to prepare you for what's coming with reactive circuit elements. And so those reactive circuit elements being inductors and capacitors. So what I want to stress actually is to pick up from what I talked about on Friday's lecture, kind of going over the unit circle and the sine function, and that all sounds kind of math related, and it is, but I think you'll see why it's such a big stress in just a moment here. At first, I just wanted to kind of let you know what sort of let's see if we are allowed to do this. What sort of things that we have in our Blackboard situation here. One of the first things we talked about in lab was periodic signals, and this is just something to review about periodic signals. When you have repeating waveforms, whether they be sine waves or some kind of other repeating waveforms, in lab we talked about ramp waveforms, or sawtooth waveforms, or they have triangular waveforms, square waves. This one is kind of square waves. Now, it doesn't look square because in reality nothing can change from, say, 0 volts to 5 volts instantaneously. There's always a rise time, and of course there's always a fall time. So people draw these things as trapezoidal waveforms instead of square waves when they're really trying to represent what's going on. Now, the period here is the time for one repetitive cell of this waveform, what we call one cycle. And the period is represented by capital T, and it represents the number of seconds in one cycle. And this is very often minuscule fractions of a second in one cycle, because we're very often talking about the frequency being a number of cycles in 1 second. So seconds per cycle, cycles per second, there's a reciprocal relationship, and of course the frequency is equal to 1 over the period, capital T, and vice versa, the period is equal to 1 over the frequency. Now, in this example, we have the period being 1 millisecond, which is 1 times 10 to the minus 3 seconds per cycle. So the frequency would be 1 over T. Well, this is 1,000ths. 1 over 1,000th is 1,000. So this would be 1 kilohertz, 1,000 cycles per second. And we talked about AC and DC parts of the signal, and I'll show you that. We have that here. There's a whiteboard about whether a signal is DC or not. There's a lot of terminology that people use here, so I just want to be careful. A lot of times people are talking about the DC component, or DC like our power supplies, where it's just a static DC signal. See this over here at 12 volts? There's no change in it. Well, if you combine a static DC signal and something like a sine wave, if the DC signal is more positive than the trough of the sine wave, or more negative than the peak of the sine wave, and those are always equal, the trough and the peak of the sine wave, well then they call it a pulsating DC signal, because this guy never actually changes direction, but he's really a combination of two signals. The average of this signal is this static DC signal. And the changing part of the signal, what we call the AC signal or AC component, is a sine wave. And so it's good to be able to understand that a signal can be decomposed in this way. Now, if you saw I assume you did, you used an oscilloscope in the lab on Friday. One of the things we didn't do, we used a signal that was purely AC. Remember, the DC offset was set to 0. But if we had a DC offset in there, the oscilloscope had one of the features for each channel is this thing called coupling. It could be AC or DC. Well, if you have DC coupling turned on, you will see the average and you'll see this sine wave, or whatever dynamic signal you have up here. That will be riding on whatever the DC component is. But if you flip the switch to AC coupling, it will ignore the DC part and the signal will just drop right down, and you'll see just the AC part. And now, why would you want to do this? Sometimes the signal's riding on a DC component for a reason, and you'd like to look at this signal, but if you have the DC component in there, this will push this way up to the top of the oscilloscope window, and you don't get to see it. You might have to even turn down the volts per division there, the vertical sensitivity, and then you can't see this very well. But if you can take out the DC, it'll drop down and you can look at this part of the signal, the AC component, more clearly. So that's something to be aware of, is that signals can be broken down into components. And an AC signal or AC component is always averaged right at 0. A DC signal, it could be the combination of a dynamic signal and a static DC signal, and you may hear people call it pulsating DC. Maybe this name is getting a little old and long in the tooth, as they say, but it was certainly the way I learned it. Obviously, DC is direct current. It doesn't change direction, so people gave these dynamic DC signals the name pulsating DC because they never changed direction. But the information that's interesting is most likely the dynamic part. And behind this red sine wave, this is our AC component. It's a dynamic signal because it's changing, and just a moment of review about the oscilloscope. This sine wave right here happened most recently. This sine wave over here, the things on the left, happened longer time ago. If you look at this faint kind of square wave here in the background, this is a pulsating DC signal because it never goes below 0. Big deal. Technically, this signal is the AC part of this signal is the part from 0 up to whatever voltage this is. Looks like, call it 8 volts. So there's a static DC signal for this square wave. It's around 4 volts. Okay, so to have a square wave stay above 0, technically it has a DC component. So just some vocabulary there, really. I just want you to be aware of that. One thing I said to everyone in lab, maybe didn't make the biggest point out of it, is some companies' signal generators, will make it seem like the bottom of the signal is where the DC offset starts. So, I don't think that's our case, but it could be. And so, you just want to be careful with a generator. Are these guys truly mathematical, and the average mid-value of the square wave, is that where we start everything, or do they start everything at the bottom? As someone who likes math, I think that you should always do it like the math does it. the average of this signal is its DC component. Yeah, right there, average. Static DC component. In this case, the average is static. All right, and so I hope that makes you aware of things. You might have to interpret an instrument that's, you know, uses a particular nomenclature. I don't like that, but this is the way I treat it, and so do many others. Certainly, you know, when presenting signals in a school, they're going to be more like mathematical anyway. So we'll see. Next thing, this is just some of these three guys right here. They're from last year. They're short little demonstration websites. This one here is this vector.js. This is written in JavaScript. If I go down here and click sine, there's your familiar sine signal, and then I run the animate button. They run a unit vector around the circle, and you can see when it gets up to 0, it starts out, climbs up to 1 at 90 degrees, back to 0 at 180 degrees, -1 at 270 degrees, back to 0 at 360, or same thing as 0 degrees. So these are this rotating vector thing generating the sine wave is it's important to us. Super important if you're, you know, in a 4-year school and you're, you know, really going to drive the dickens out of this stuff. But you know, it's important for us too, because this rotating vector has a name. It's called a phasor, and this is important, this phasor thing. If I'm starting here, like this is time 0, see the time down here at time 0? If I swing through 0 at time 0, then my phase is 0 degrees. In other words, I swing through 0 at time 0. Now, if I had started, if I swung through 0, if I shifted this thing, say, to the right, and I swung through 0 at, let's say 60 degrees, then I would say my sine function has a phase of 60 degrees. So very typically people, you know, we will talk about sine waves with phases, okay? And so you'll see it as we go along, but just remember that this is a true sine wave. It has 0 degree phase. A sine wave that has, say, 60 degrees phase would be written as sine of theta minus 60 degrees in the parentheses, okay? Because mathematically you'd have to start it off late. And so keep in mind that the sine waves we work with could be shifted in time. So they're beautiful sine waves and everything, but they're either delayed or seemingly advanced, okay? Phase is an important thing. And then they have these, I don't know, rotating vectors. They're called phasors. We won't dive into phasors, but you'll see that when we compute things, we have to keep track of phase. Okay. Let's see, there was another one down here. Is this one any good? Oh, this is a guy that talks about it after some commercial here. There we go. We have our Audi. Okay, great. And this guy talks about an animation, and he actually does the same thing, and that's great. Illustrating sine of x, and he's using some Wolfram, the Mathematica people. to describe it. I won't go through that right now. So there's vector.js, there's math is power for you, and there's this Desmos is a calculator online. It's a rotation thing, and I think that if you go down here to sign animation and you check this, you'll see that it starts out with 0 height, gets up to 1. Let's see, can I reset that thing or something? Crap, I didn't mean to do that. Here, so here's the rotating vector. And let's see if I can time it so I can, as he comes around to about here, it should be 0 height here. And it just draws a whole sine wave. But you can see as it rotates around, the height is recorded over here, and that's a sine wave. Okay, there he goes. Yeah, I guess it erases and redoes itself. So you can watch this thing and see that the altitude right here is the sine part. Okay, and if I put in, let's say I take out the sine, and let's say I put in the cosine rotation. Well, cosine starts at kind of at 90 degrees of a sine wave. It's very similar to it. You can see the shape is the same, but it has a different phase. It's advanced by 90 degrees, or you could say it's delayed by 270 degrees. Either way. And in a lot of people, the way they demonstrate, I should find one of these. The way they demonstrate cosine is they'll have sine as this altitude, and they'll draw the cosine going down here because the cosine represents this part of it. Okay, so when this guy gets to 0 degrees, cosine would be 1. When he gets to 90 degrees, cosine would be 0. Over here would be -1. It would be 0 again, and it'd come up to 1. All right, so that's that. So I'm just trying to show you ways that you can see this unit circle to trigonometric function kind of a deal. We talked about the ratios of we talked about how ratios from that unit circle, how the ratio of the altitude, the height, to the vector itself, which in our case is a 1, so it makes it really easy. The ratio of the height to the hypotenuse of the triangle formed by that rotating vector is, and you can see that here, trigonometric ratios and right triangles. That's how you get these sine functions and cosine functions and everything. The other thing about the unit circle I just want to say is that, you know, we make electricity with generators. We rotate wires in magnetic fields, and as the wires cut, we get magnetic induction. And because we do it in a spinning fashion, a circular spinning fashion, we wind up getting a sine wave out. It's not, not trying to make that statement like it proves anything, but in you know, there are animations out there where people take one loop of wire and spin it in a magnetic field. I've done it in some PowerPoints I've made for the introduction to you know, electronics for technicians 1. So spinning a wire in a circular way, or like a loop of wire in a magnetic field, will generate a sine wave. And so, you know, I think maybe even Cengage makes that point. So let's go a little farther now. We know what trigonometric functions are. They've talked to us about them in, you know, starting, I don't know, probably middle school. And so we have them here. We have this rotating unit vector, this unit circle that it all comes down to. Let's look at some things about these sinusoidal excitations, that, you know, excitation meaning to excite your circuit. let's take a look at that stuff and see how it is played out in practice. Here's a little review for some things I've said before. Important, of course they're important things, you know. If I have a purely resistive circuit and I don't know, I give it some complicated excitation signal, resistors, you know, turn electrical energy into thermal energy or heat immediately. So what I get out is a copy of my input signal, likely to be scaled. It's the same waveform, it's just scaled, and there's no delay. All we did is make some heat immediately. Might be microscopic amounts of heat or whatever, but you know, just we made some heat. Nothing happened to this signal in a resistive circuit. Now, if I take some arbitrary excitation waveform, and let's make that point. This is an arbitrary. So it could be something like this waveform. If I take that waveform and I put it into a circuit that has resistors, inductors, and capacitors, which the real world does, what will happen is, as we said before, the resistors don't create any delay. They do their thing immediately, no problem there. But inductors store up magnetic energy and release it back. Capacitors store up electrostatic energy, like charge, and release that back, and it'll just completely skew and smear our waveform all over the place. And so we'll get a different waveform with some scaling. Parts of the signal may suffer more or less delay. We're not going to get the same signal out, period, end quote. Okay, so it's a different waveform in this case. Then, you know, back to how fantastic sine waves are and all that kind of thing. The one function that really, well, it really helps us analyze these circuits, because if I put in a sinusoidal excitation, this could be a sine wave or a cosine wave, or they're both sinusoidal, or any wave with that shape. It could be a sine wave that's been delayed by 15 degrees, I don't know. But if I put that into an RLC circuit, I will get a sine wave in. So, you know, sinusoid, let me get down here. Sinusoid in results in sinusoid out. That's a really cool property. Mathematics like to refer to the sinusoid, in this case, as an eigenfunction. Eigen is a German word for truth. And so what it says is this function reveals, you know, what's going on in here, because it comes out with a sine wave. It may be scaled, maybe less, it may be delayed. Okay. In fact, on the oscilloscope, sometimes it'll actually look like it's advanced. It's kind of a funny thing, and so you get into a little philosophical, you know, treatment there. But let's head back toward some, I don't know, Ohm's law kind of a thing. All right, and here we go. Now, we know what resistors do. They turn electrical energy into heat immediately. No distortion, no delay. Okay, I told you I was going to tell you that over and over and over again. Inductors, not so much. We know that because of inductors have this Lenz's law property. They you put some current into them, or you cause a current to flow in them. Inductors do not like changes in current. Okay, you know, let's inductors oppose changes in current. You know, there's a lot of duals in this stuff, if you know what a dual is, a D-U-A-L. Capacitors, it turns out, in fact, I'll add another statement here. Current lags in inductive circuits. Good thing to memorize. It kind of goes right along with the fact that inductors oppose changes in currents. So if there's some timing involved, you could believe that the changes in current were delayed. And so we come up with this thing to say current lags in inductive circuits. So we know that when we try to change the current through an inductor by some means, the inductor says, look, if you're going to add current, you're going to create a magnetic field. The lines of that magnetic field are going to fall across that inductor itself, and it's going to generate a back EMF, back electromagnetic force, or back voltage, and that back voltage is going to fight you, all right? And it has to be that way. If it's going to be some way, it has to be that way, because if it helped you, you'd wind up with a perpetual motion machine. So in inductors, and like Lenz's law says, any change in current and that change in magnetic field fights you. It generates a back EMF. It induces a back EMF, if you will. If you try to reduce the current, same thing. The inductor says, I've got a lot of current flowing in me. I don't like changing it. So if you think you're going to reduce that current very quickly, or even at any rate, I'm going to, I'll collapse my magnetic field, and I'll generate a back EMF or back voltage against you, reducing my current. And I'm going to put some more things up on this unit. We had that demonstration in lab on Friday. I took a big honking inductor and just a little bit of resistance. I put like an amp through the inductor, and I remember I had a voltage divider so that I could look at the output of the inductor on a scope when I broke the current. And we had, I saw one as high as 1,000 volts of a negative spike, an inductive spike, and I think we all saw one of 800 volts. There were some that were like 200 volts, there were some that were 3 or 4 or 600, but it wasn't too many times before we could get like an 800 volt spike on there. And that's, with my fooling around with a clip lead on the inductor, you could see some sparks coming, because as soon as I tried to break the circuit, that voltage on the inductor went super low, creating a big voltage difference across the air gap. So if you try to take the clip lead or the metal contact away slowly, you'll see that it will spark and arc, as they say, because the voltage gets high enough to break down the air between the inductor terminal and the clip lead that I was, alligator clip that I was using to put that current in the inductor. Again, I will post that stuff in a way that you can find it in the same module in Blackboard. So let's talk about these inductors. And what we're doing is we're talking about sinusoidal excitation, and we're talking about having that excitation on the circuit for a long time. So there's no, if I try to just start up a sine wave on an inductor, I'd get some kind of response from the sine wave, but I'd also get some response from going from nothing to putting the sine wave on. So let's forget about that moment. Let's say the sine wave's been, on the inductor or inductive circuit for a while. So in this case, we would call this kind of analysis AC sinusoidal steady state, or steady state sinusoidal. Maybe that's sorry. So sorry. We would have AC steady state, meaning it's been going for a long time. It's, you people put up with me. It's been going for a long time, and it's all settled down to what it's going to do. So AC steady state sinusoidal, analysis, if you will. And what's cool about this is, if we had to do anything other than the steady state sinusoidal, we'd have to know calculus and all that stuff. But with these sine waves, we can get a lot of information about a circuit out, and it allows technician level people to analyze circuits without having to do a lot of calculus, without having to do any calculus. Excuse me. All right. And you can thank a famous inventor named Charles Proteus Steinmetz for this. He used to work in Schenectady for GE a long time ago, so not very far away. And he's the one that proved that this all could be a way to analyze this stuff. Now, the U.S. power frequency, if we look at the electricity that comes out of the wall, wait a minute, I guess I'm jumping ahead. So inductors in the steady state thing, they have a kind of AC resistance, if you will. And we can't just, put these things together like the nice resistive circuits where two resistors in series, you could add them together, or two resistors in parallel, you could do product over the sum. This is where the vector stuff hits us. But fortunately, there's a way to deal with it. Did I turn my 2 into an A? Okay. So in the AC steady state sinusoidal analysis, inductors have a kind of AC resistance. We call it inductive reactance. All right? And instead of resistance, this is called reactance. So, since inductors are signified by an L reference designator, X sub L is the inductive reactance. And we can compute it. It's equal to 2 pi times the frequency of our sinusoid times the amount of inductance in the inductor. Okay? The unit of inductance is henries. I don't know if you might see henries in a power supply, but typically it's millihenries, microhenries, nanohenries for high frequency circuits. So here's the frequency of our sinusoid, how many cycles per second, and here's the inductance. Now, as I started to say before, the US power frequency is 60 cycles per second, or what we call hertz, right? I think this unit right here, I didn't say enough about this back a while ago, but this is called hertz after Heinrich Hertz. Okay, mentally you can think of it as 60 cycles per second. Here you can, hertz is just a unit they give to it to give honor to old Heinrich, baby. All right. For example, a 4 Henry inductor. This would be a big honking inductor. Find XL, at 60 hertz. This number in Europe, by the way, I think, oh no, my memory's going, I can feel it. In Japan it may be 60, but in Europe it's 50. So important thing to note, just to make a note of. If you're working on some equipment for the US and for Europe, they have ways of making power supplies now that either can take either 50 or 60 hertz without any degradation, or some of them have a switch that'll flip from 60 hertz to 50 or vice versa. 4 Henry inductor at 60 hertz, so I have 2 times, and let me get my calculator out here, clear all that stuff. So what do we want to do? We want to do 2 times, for me pi is a blue, one of those shift buttons, and that's not easy to see, is it? Let's see if we can get a better focus on that. Oh, that's great. There's probably some brightness thing that I can set, but well, it's 2 pi times the frequency, which is 60, times the inductance, which is 4, and I'm getting, as I read this, about 1.51 kilo ohms. So when you do this, you'll get about, mine came out like 15079, so I called it 1.51 kilo ohms. Now here's the thing, this is the big difference. Resistance because it doesn't cause any delay or anything like that, resistance is always at 0 degrees. Inductors are always at plus 90 degrees. All right. So here I am. You know what I'm going to do? I'm going to have to add something whose steady state sinusoidal resistance is at 90 degrees with something whose resistance is at 0 degrees, and that's going to bring in vectors. So here we go. As I come down here, this is what's called an impedance chart, and reactance goes up this way and resistance goes this way. Some people say that this is like complex numbers, where the real part is on the x-axis and the imaginary part's on the y-axis. You can say, well, reactance is on the y-axis and resistance is on the x-axis. So if let's see if I can zoom it all on this thing. Can we do that? Okay. So let's see. I have like 1, 2, 3, 4 ticks to make 1 k ohm. So there's my R1. There's 1 k ohm. And this inductor is like 6 ticks because he's like 1.5 k ohms. And how do I add these two vectors? This guy's at 0, this guy's at 90. Well, the way to add vectors is you use the parallelogram rule. Now, we're very fortunate here because these two are at right angles to each other. So if we want this distance right here, this is called z total, and I'll tell you why. This guy I guess that's about as good as it's going to be on focus. Yeah, it's even worse. So this guy is the hypotenuse of a right triangle formed by the inductive reactance XL, there it is, and the resistance R. Now let's see if I can move this. Yeah, R. So if I move this over here, the old Pythagorean theorem says that if I take the square of the inductive reactance and I take the square of the resistance, that's like the square of this leg and the square of that leg, I'll get the square of the hypotenuse. And so I would get zt squared, but I took a square root of this whole mess. So I have let's just say it's 1.5 k ohms vertical and 1 k ohms horizontal. And if I compute that, I will get let's see, I'm gonna do the square root thing, and then I'm going to do 1.51 x squared plus 1 x squared. I'm going to get out from underneath the radical and then hit the sign, and I get 1.811 k. And here, this, I guess the last time I did it, I got 8.03 k, but let's say it's around 1.8 k. And now this thing, what is this thing called? When I have just an inductor, it's called reactance. When I have reactance combined with resistance, right, is called impedance. And it gets the letter Z. Now you could argue that each of these is vectors. XL is a vector, and R can be a vector. You know, if I say this is 1 k ohms at 0 degrees, XL is 1.5 k ohms at plus 90 degrees. So when I'm not at 0 or 90 and it's a combination, then I have what we call impedance, and it too will be a vector. But the magnitude of the impedance, so remember what Cengage says, vectors have magnitude and direction. The magnitude of the total impedance in this case is computed by this, and it's approximately equal to 1.8 k ohms. That's the magnitude. But what about the angle? Well, See that theta symbol right there? This is the opposite, okay? That's XL. And this is the adjacent down here, which is R, okay? And we know that tangent of theta is equal to opposite over adjacent, right? Let's see. Maybe we can. So the tangent of theta is equal to opposite over adjacent. You know, we would write this as, you know, tan theta, okay? So that's equal to that. Great. So I don't want the tangent. I got the tangent because I know XL and I know R. I want this angle. So remember that some of these functions have inverses, and they'll call them, say, arctan. Okay? So theta equals the angle whose tangent is opposite over adjacent. All right? If I knew theta, I could tell you the ratio of opposite over adjacent. It would be, you know, the tangent of theta. But we have these guys, and we want theta. So we're going to use the angle whose tangent is this stuff. And when you put this in here as 1.51 k ohms over 1 k ohms, well, that is pretty crappy to read. And you use your calculator, you know, in degrees mode, or if you were to look this up in tables, you would find that theta is equal to 56.5 degrees. Okay. And so that's a pretty interesting thing. It means that it just means that the current flowing through here is, you know, 188.9 milliamperes, because I still got Ohm's law. It's still true, but these are now vectors. Okay. So what I should do here is I should take into account the magnitude and direction. So this guy up here, usually the voltage we apply is always at 0 degrees. Okay? And this guy here is at plus 56.5 degrees. All right? So now I compute this. This will come out to be my 188.9 milliamperes, I believe it was. Just 2,000 into here would be 170, but it would be milliamps. So I think I had this wrong. Let's calculate that the proper way. You know, 3.4 times 10 to the 2 divided by 1.8 times 10 to the 3 is equal to do that. I'm going to get 3.4 divided by 1.8. So I'm going to get 1.89, we'll call it. Let's round it off a little sooner. 1.89 times 10. Now this, we subtract the powers of a like base when we divide, so that becomes times 10 to the minus 1, which would be equal to 0.189 amperes, and that's equal to 0 milliamperes at power of 3, so I would go over 1, 2, 3, the power of minus 3, I'm sorry. So this would be 189 milliamperes. But what about the phase? Well, it's interesting. Phases are like exponents. When you multiply or divide, you add phases when you multiply, and you you subtract phases when you divide. So this guy will now be equal to 189 milliamps at negative 0 minus a positive 56.5 will give me negative 56.5 degrees. And remember, I said that, and that's I total. So here's I total, and we'll just kind of put a little box around that. All right. So I total is 189 milliamps, but he's behind in phase by 56 degrees. And what did we say about inductive circuits? We said current lags in inductive circuits. So if we drew this thing, well, let's do one more thing. I'm going to go here with number 3. This will make it a little easier to believe. Remember, we had this, this was our circuit. Okay, R1, 1K ohm. L1, 4 Henries. And this guy was 340 volts peak to peak at 0 degrees, and it was 60 hertz. Okay, so now we know the total current. We know the current that flows here. And what's weird is this current is out of phase with this voltage. Okay. So if we call this node A, and we call this node B, and we say, if we wanted to look at the current on an oscilloscope to see it behind, we could look at the voltage, we could look at VB, okay? And here's why. VB, it's a vector, is equal to V equals IR, right? And the current flowing through this resistor is our total current, IT. Okay? So I'm just going to multiply IT times R, and that's equal to 189 milliamperes at minus 56.5 degrees times 1 k ohm at 0 degrees. It's a resistor, right? Well, let's work this out. Milliamps times k ohms. This is 10 to the minus 3. That's 10 to the plus 3. So we could say, let's just do it anyway to make it clear. This is times 10 to the minus 3 amperes at minus 56.5 degrees times 1 times 10 to the 3 ohms at 0 degrees. Okay, so when we multiply these two together, 1 times 189, I'm going to get 189. And this is really, now there's something I didn't do here. Because these are volts peak to peak, let's be back here. These are volts peak to peak. These are amps peak to peak and milliamps peak to peak. All right. So this is doctor this up a little bit. This is minus 56. So this is amps peak to peak. Or milliamps peak to peak. This is amps peak to peak. And so what I'm going to get here is 189. Now the 10 to the minus 3 and the 10 to the plus 3 cancel out. The 1 times 189 gives me 189. So I've got 189 volts peak to peak. That's 189 volts peak to peak, and when I multiply, I add the numbers, and so this is just 0 plus minus 56.5 degrees, and that's V VR1. VB is the same thing as VR1, and there's your answer. So if I graph this thing, and let's say this is 340, here's volts peak to peak, and this is time, or, well, yeah, on an oscilloscope it would be time, so let's do that. So this is time. Now the applied voltage starts right at 0, and I'll put in and let's see how bad I am at drawing a sine wave. So the voltage still pretty bad. All right, so this guy right here is this is our source voltage. It's so sorry. 170, and this is minus 170, and that gives me 340 volts peak to peak. Now, this is 90 degrees, and this is close to 60, so this guy starts, you know, maybe, I'm going to divide this through, just pretend that this is 56.5 degrees, let's say late, okay? So now the voltage is going to be at about 90, it's going to be at like 89.5. Because we got it, let's see, 189, yeah, volts peak to peak. So we're now going to get somebody who starts here and comes back through there. So let's see, I'll try to do this maybe with dotted lines. So if this is, so this is 60 and 90 would be 150. So this guy will reach its peak maybe about here. So he'll be coming like this. And this guy right here is VR1. What's nice about having the resistor in this portion right here is that because the resistor is 0 degrees and multiply it times the current, I get the timing of the current waveform. You know, anything plus 0 degrees is itself, and so I get that. And so this is VR1, and you could say on a different scale, if I put, you know, I don't know if I put milliamps in here, I guess this would also be IR1, but I you know, this is volts peak to peak, so I won't do that. But you can see that I have my driving source waveform is here, and the voltage across R1 is late because the current through R1 is late. So now this isn't quite right over here. I guess this should have gone down more like say that. But hey, look at this side over here. So there's an example of what happens to us in a steady state AC sinusoidal analysis of a circuit. And the one last thing I'll say about this, and I will be putting up, or I think we already have, resources for this, is that every periodic waveform can be decomposed into a number of sine waves, possibly an infinite number of sine waves. So even a square wave can be built from an infinite number of sine waves if they're all at, in the case of the square wave, they all have zero phase. They're all at 0 degrees. And it's only the odd harmonics. So you take a sine wave. We'll see this, but my point is, you can break any periodic waveform into a bunch of sine waves, and you can now analyze what a circuit's going to do at a given frequency with sine waves. You know, if you automate this in a computer program or something like that, or a spreadsheet, you could put in some low frequencies and see how they do, some middle frequencies and see how they do, and some high frequencies and see how they do, and gain a lot of understanding. And you didn't need any calculus at all. You might not be able to tell me exactly what that complicated waveform will look like when it goes through the circuit, but you can tell me that the high frequency parts of it will be maybe squashed, and the low frequency parts will make it through okay, and you know, that sort of thing. And we can demonstrate some of that. We'll also do a parallel example. We're not going to go into, I don't think Cengage goes into combinational circuits with this. You could see it could get into a lot of work. There's a lot to it. That's great for 4-year students, but what we want you to understand is what inductance does to a circuit, and what capacitance, when we get to that, will do to a circuit. And that's what this is all about. So I will scan these notes and of course capture this lecture, and we'll put it on the page there. And I'll probably be digging up some worked examples that I have and posting them as well, so you can see. Maybe I'll even record, you know, just to show you the examples, and you can go through it with me and see this stuff. It's a mess in a way, but it's not that much of a mess, and it shows you what happens to it shows you what happens to individual sinusoids. But you know, if you could simulate it, you would see what happens to sinusoids of all frequencies, and you know, that'll give you some intuition for what that circuit is doing. Okay, let's call it a wrap there, and we will go on with more AC steady state analysis and this idea of inductance and what it does to us. For one thing, you'll see that when the voltage and the current are out of phase, you do not have a full power delivery thing. You have what's, you know, this thing called imaginary power or reactive power, and it's the kind of the power that's waiting. It's been stored in components and it's coming back out. And so at any rate, right angle trigonometry abounds in computing this stuff, and will help you see it. Okay, great, and see you next time. Take it easy.